Bismillahirrahmanirrahim. Assalamualaikum and a very good day to you all. In today's video, we're going to talk about relation of the variables from chapter 12 from Shigley Mechanical Engineering Design book. So bear with me. This video will take long time because you want to do the calculation, the examples and everything. And I suggest that you have the textbook beside you. Uh, because you want to refer a lot of figures, a lot of graph and everything. So the chapter begins with solving Reynolds equation with iteration technique. Okay. Before proceeding to the problem of design, it is necessary to establish relationship between these variables. This person, Albert A. Raimondi and John Bell of Westinghouse Research Laboratories, use iteration technique to solve Reynolds equation on using digital computer. Okay, so using computer they can do much more analysis. Of course, using computer will benefit you a lot. Okay, so Raymond and Boyd papers were published in 3 parts containing 45 detailed charts and 6 tables of numerical information. In all 3 parts, charts are used to define variables for length to diameter, ratios 1, 4, 1, 2, and 1 for beta angles 60 to 360 degrees. Okay. Under certain condition, the solution to Reynolds equation give negative pressure to division portion of the oil film since the lubricant cannot usually support tensile test. Okay. So of course, because tensile test, when you go to the UTM machine, which is universal testing machine, that machine will try to elongate it. Okay, liquid lubricant, of course, cannot elongate. Okay, it cannot be seen as elongate, so it cannot support the tensile test stress. Okay, so part 3 of Raymond uh, board papers assume that all film is ruptured when the film pressure becomes zero. Okay, when the film pressure becomes zero, oil film ruptured, no oil film. Okay, part 3 also contains data for infinitely long bearing. Since it has no ends, means there is no side leakage. It is assumed no side leakage. Okay, it is assumed no side leakage. See, here is my cardboard. Okay, let's say this is a general bearing. It is assumed there is no end left, there is no end at the right. Okay, there is no side leakage at the left hand end. Okay, we assume to make the calculation simpler. The charts appearing in this book are from part 3 of the papers and are for full general bearings. Beta equals to 360 degrees only. Space does not permit for inclusion of the charts for partial bearing. This means you must refer to the charts in the original papers with beta angles less than 360 are desired. Notation is very nearly the same in this book as no problem should arise. So, for this video, okay, from using Raymond Benedict papers, meaning that you consider the general bearing is already full. Okay, you have already inserted the lubricant here, and this general is full of lubricant. Okay, that is called 360 degrees. Okay, while it is being put, meaning that initially that you start working, you pour lubricant inside it. While the lubricant is being full to 360 degrees, it is partially full. That is not covered in this Renault Renault board equation, Renault board graph. Okay. Uh, okay. One of the most important assumptions made in Raymond D. Boyd analysis is that viscosity of lubricant is constant as it passes through bearing. Okay, but since the work is done in lubricant during this flow, the temperature of oil is higher when it leaves the loading zone than it was on entry. Okay, The viscosity chart clearly indicates that the viscosity drop off significantly with a rise in temperature. Since the analysis is based on constant viscosity, our problem now is to determine the value of viscosity to be used in the analysis. Okay, this slide tells you about assumption by Raymond and Boyd saying that viscosity is constant. Okay, viscosity is constant when it come into the left, going up to the right. Okay, purpose to make assumption is to make a simpler calculation. Okay, it is okay to do that. Everyone does that. Okay, uh, in uh, in actual practice, okay, in actual practice, when the viscosity enters here and we go out, along the way, process will happen, the loading, the temperature rise and everything. So number one, temperature going in and temperature going out is different. Okay, temperature going in is low, temperature going out is high because many process happen along the way. So the temperature going up, okay, slightly higher and everything. Okay, number one. Number two, when the viscosity come, okay, and all the process happen, the temperature rise and everything, the viscosity going out is lower. Okay, it's become lower. Okay, let's for example imagine your car doing services. When you do your service, you use 5,000 kilometer oil. Okay, after a while you do service your car, the viscosity of that oil lubricant that you use for your engine has become lower, and then you have to change. This is what this means. Okay, this is what it means. Okay. Okay, about side flow. Some of the lubricants that enter the bearing emerges as side flow, which carries away some of the heat. The balance of lubricant flows through the load bearing zone and carries away the balance of heat generated. In determining the viscosity to be used, you shall employ the temperature that is average of the inlet or temperature average. Temperature average is equals to T1, which is inlet temperature, plus uh, difference in temperature ni AT over 2. Okay, the symbol the symbol variation, the variation in temperature over 2. Okay, so when it when something coming on the side, it will come on the other side. Along the way, it will collect all the heat and it will go out. Okay, it will go out. The heat generated will come out with the side flow. Okay, so we want to know what is the average temperature because the heat coming in and heat coming out is different. Okay, so in order to use the graph by Raymond and Boyd, we have to know the average temperature. Okay, so the average temperature is given by the equation 1214. Variation on viscosity. So viscosity varies considerably with temperature in a non-linear fashion. So what is the mean by non-linear fashion? Imagine you are boiling your water. Okay, when you boil the water, as temperature rises, it will eventually risen the temperature in a linear fashion. So when it reaches 100 degrees Celsius, it will boil. Okay, the water will boil. But with viscosity, it is not like that. It will go up and down until you cannot easily determine the viscosity. Sometimes it's going up, sometimes it's going up linearly, sometimes it is random fluctuate. Okay, so figure 12 to 1212 until 1214 is not logarithmic as the case of differing vertical length. Okay, if you have the textbook with you right now, you can open and you can see figure 1212 until 1214. Okay, there are graphs that we will learn after this. Okay, this graph represents the temperature versus viscosity function for common grades of lubricating oils in both customary engineering and SI unit. We have temperature versus viscosity function only in graphical form unless curve fits are developed. Okay, you see table 12.1. Okay, if you have the textbook with you, you can see where is the table 12.1. One of the objective of lubricant analysis is to determine the oil outlet temperature when oil and inlet temperature are specified. Meaning that when the oil, okay, when you put here, when you the inlet is here, okay, and when you up come here, you can determine temperature. Of course, you can determine the temperature here, inlet, but the outlet, what is the temperature? This is what the graph can determine. Okay, in analysis, temperature rise will be first estimated. This allow for viscosity to be determined from the chart. Okay, then with the value of viscosity, the analysis to perform. The temperature rise is then computed with this new estimate. The temperature rise is established. This process continue until it is estimated and the computed temperature agree with it. Okay. Okay, to determine oil temperature. Okay, to illustrate, suppose we decide to use SA30 oil in application with oil inlet temperature is 180 Fahrenheit. Okay, for a Malaysian student, uh, for countries that does not use Fahrenheit, the approximate value to convert is around 33 something. Okay, uh, this is I listed here 185 Fahrenheit equals to 90 degrees Celsius. Okay, 207 Fahrenheit equals to 96 Celsius. Okay, so if 180 Fahrenheit, the value must be lower than that, lower than 90 degrees Celsius. Okay, so this is the oil temperature we estimate is 180 Fahrenheit. Okay, so temperature rise using temperature rise is variation temperature is 30 Fahrenheit. So the average temperature we from this equation, 12 and 14, you get this value of 900 195 Fahrenheit. Okay, from figure 12, okay, after this I show you the line. Okay, follow the SA30 line. Okay, the way to do it is to follow the line first and find out that the mu is 140 mu rand. Okay, which is rand is a unit for viscosity at 995 degrees. So we use this viscosity 1.4 microrand in analysis that we explain later. Okay, and we find out that temperature rise is actually 54 Fahrenheit, 54 degrees Fahrenheit. So you put again in this equation, you get the temperature rise is actually 96 degrees. Okay, if you have the textbook with you, open the textbook and see the figure 12. This is the figure 12. How uh, this is the way how you do it. Okay, given, let me explain back the example given in the previous slide. Okay, the temperature rise using the equation where you get the temperature is and then in the end you get the temperature as 195 degrees average temperature. This is approximately 195 degrees. At you see the number 200 here, that 195 degrees is approximately here, and then you extrapolate the line until you get SA30. So we, because we use SA30 oil in this question, where is SA30? 1, 2, 3. Here is SA30, and then we extrapolate here until we get approximately 1.4 rand. Okay, so in the exam, any value that is in approximate is accepted. Okay, so now we accept 100 1.4 microrand. And then uh, the slide mentioned that we use uh, we use analysis. Okay, and then we get another temperature, average temperature, which is around 207, like at this point. Okay, and then again you can extrapolate, and you can extrapolate and you get another value for micro. Okay, so this is how you do this example. This is how you read the viscosity temperature chart. Okay, so this correspond to point A on figure 1212, which is the figure in the previous slide, which is above SA30 line and indicates the viscosity used in the analysis is too high. Okay, then if you are not satisfied with the viscosity, and you may use uh, another viscosity of your choosing. Remember, in the first try we choose 1.4 microran. Okay, and then we try one microran. Okay, then we run through the analysis, meaning that you extrapolate the graph. Okay, you see the graph is microran versus temperature. Microran here, temperature here. Okay, you extrapolate the microran one, and then you come into the SA30 line, and then you go down to see the temperature. What is the temperature? You get 195 Fahrenheit. Okay, if the points A and B are fairly close to each other and opposite side of the SA30 line, the straight line can be drawn between them with intersection locating at the correct values of viscosity and average temperature is used in analysis. For this illustration, we can see from a viscosity chart, they are 200 203 Fahrenheit, and microran is 1.2 microran. Okay, okay. Here are figures in the textbooks that I copy here. Shows that figure 1213, viscosity temperature charts in SI unit. Previous now we use the temperature chart in Fahrenheit. Now the same chart in Celsius. Okay, for countries like Malaysia, we use Celsius. Other countries that use Fahrenheit, they use Fahrenheit. No problem. Okay, uh, you can see in the next slide, which is figure 1214, which charts for multi viscosity lubricant. You may familiar with the this number 20W50 to 20W40. You remember when you go to your mechanic shop, want to change your uh, car oil, and okay, and there are many variation of lubricant. Okay, and that oil shows the number 2040, 20W50, 20W40, and others. Okay, this is determine the viscosity of the oil. Okay, whether you want your car to be serviced 5,000 kilometer, to be serviced 10,000 kilometer, and others. This is depend on the viscosity of the oil. This is called the multi viscosity lubricant. Okay, the way to analyze it is is simple. Is just read the chart like this. Okay, just like I show you in the previous slide. Everything it's like that. Simple. Okay, this is the curve fits for approximate viscosity versus temperature function for SAE grades 10 to 60. Okay, you see this is the oil grade. You see the viscosity in rand, and this is the constant temperature in Fahrenheit. Okay, meaning that the maximum temperature, if you are your engine operate at high temperature, you should choose better grades engine. Yeah, okay. Let's say you have a small car, only operate a short distance. Uh, just you can choose lower grade oil. Doesn't matter. If your car operate a long distance, you want to go a long distance, better you have better grades car because the temperature will rise. Okay, and everything. This is the grades of the car of the lubricant, And then this is the 12 figure 1215 shows the polar diagram of film pressure distribution using notation. You remember the word wedge? Okay, the word wedge, WEDGE. In this preview, in other previous video, I mentioned the word wedge. Okay, meaning that when the lubricant, okay, let's say this is the general bearing, let's say this is the shaft. When the the general bearing go up and down, at the moment going up, that doesn't matter going up or down, and at one moment it reaches the maximum peak. Okay, at any point the pressure distribution is like a wedge shape. It's like a wedge shape. If you can open back among the first videos on this explanation on Buckham Tower theory, I have explained about this video on pressure distribution, where uh, from historical Beacon Tower, he done experiment on corkscrew. He make a hole at the corkscrew, okay, and when he try, he made a hole at the shaft, and put when he want to close the the hole using corkscrew, using anything that he want to in order to close it, then the pressure distribution is too high that the corkscrew travel fly away. Okay, this is called uh, polar distribution, and this is the basis of the theory on hydrodynamic. Okay, you should open back the previous videos on. I talk about a lot about this uh, hydrodynamic theory. Okay, in the end, the shape, the pressure distribution shape is become the wedge shape. Okay, and this is a figure 1216, chart for minimum film thickness variable and eccentricity ratio. You see here, uh, this chart and everything we will explain later when we are doing the example. Okay, chart for minimum thickness, you see here, the most important thing is the bearing characteristic, the Sommerfeld number, R over C, power of 2 U N over P. Okay, you will know about Sommerfeld number. You must know about Sommerfeld number. This is the x-axis graph, and then the y-axis graph you see here is the minimum film thickness, meaning that what is the most minimum that it can be. Remember, we want to avoid metal to metal contact. Okay, we want to avoid metal to metal contact. We have no choice. There must be a gap. The gap we cannot see with our eye, but it is a gap. The lubricant is the gap. So this is called minimum film thickness. Okay, and then this is the okay, and then this is the chart for determining position of the minimum film thickness. So again, the bottom one is Sommerfeld number, and this is length over diameter ratio. Length over diameter ratio is 1, 1 over 2, 1 over 5. Length over diameter. Length, length. Okay, this is the length. Suppose this is the length and this is the diameter. Okay, you divide and you know what is the length over diameter ratio. Okay, and then this is the position of minimum film thickness data degree. We will learn later after this. Okay, you will learn later after this minute location of minimum film thickness. Okay, the remaining charts from Raymond, Lee, and Boyd relate several variables to the Sommerfeld number. These variables are minimum film thickness, okay, figure 1216 and 17, coefficient of friction, figure 1218, lubricant flow, figure 1219, 1220, and film pressure, 1231 and 1222. Figure 1215 shows the notation used for the variables. We will describe the use of this curve in a series of 4 examples. You do a lot of example. This is a lengthy video, okay. Minimum film thickness, variable has not and concentricity E, okay, plot against homomorphic number with contours for various values, okay. So we are going to do example 12.1. 12.1 is important because it will show how to use the graph. Okay, so 12, example 12.1 says that determine H naught, which is the minimum film thickness, and eccentricity E using the following given parameters. U, the viscosity is 4 microran, N is the revolution, okay, is 30 revolution per second, and W is the load of the bearing load is 500 pound. R is the radius of the journal. Let's say let's say this is the journal. My marker pen is the journal. The radius of the journal is 0.75 inch. This is the radius. The diameter is 2 times uh, 0.75. And C is the clearance. Okay, C is the clearance, and L, the length is 1.5 inch. 1.5 inch. Okay, the length. Let's say this marker is a general, is a general shaft. So the length is 1.5 inch. Okay, so the solution. The solution we involve using figure 12.16. This is the figure 12.16. Okay, before doing that, you must know the nominal pressure because you want to put it, this value, into the Sommerfeld number here. The P here, you want to put in the Sommerfeld equation here. So what is the P? P is the nominal pressure, load over 2 RL. Okay, from the equation you will get 222 PSI. Okay, and the load is the weight of the shaft. Okay, the Sommerfeld number from equation 12.7, when n is nj equal to revolution per second, nj is revolution of the journal. This is the journal. Journal also is called a shaft. In this topic, the shaft is called a journal. So s equal to r over c, power of 2 micro n per p. You put all the equation and you get 0.135. This is the Sommerfeld number. Okay, you must remember the equation Sommerfeld number. Okay, also L over D equals to 1.5. This is important because of the option for figure 12.6, there are 4 options. L over D equals to infinity, L over D equals to 1, equals to 1.4, 1.5, and everything. Okay, you can see, and because you want to extrapolate the graph, and S equals to 0.135, L over D equals to 1, which give the H naught over C equals to 0.42, and E equals to 0.58. And then quantity H over naught over C is called the minimum film thickness, which is H over naught is minimum film thickness over the clearance. Okay, let's see. This is the figure 1230. If you're not familiar, what is the term C, what is the term R, you can see this picture. Okay, from figure 1230. Okay, this is the figure 1216. Okay, basically it has the Sommerfeld number. Remember that in the previous slide, you calculate you calculate the value pressure P equals to W over 2 RL, something like that, and then you get the value P, and then you get the number 0.135, approximately at here, 0.135 like here, and then extrapolate until you get 1, because L over D equal to 1. Okay, and then you get extrapolate here. Okay, you get here R not over C, you get this number. Okay, you get this number. This is how you read the graph. In examination, it will be a lengthy and thick, because we have to put this graph in attachment. So uh, it will also be a lengthy calculation to do all the answers for the uh, question. So you have to know, first, one thing, you have to know the Sommerfeld number. Never forget to calculate the formula for Sommerfeld number. And then you have to know how to read the graph, because everything is connected. You will start with 1216 up until 1220 something. Okay, the figure 1216, you begin with figure 1216 until the final figure 1230 something. Okay, note that if the journal is centered in the bushing, eccentricity it becomes 0 and h naught becomes c. Okay, you see in the figure 1230 here, this is the figure 1230. Okay, imagine the journal is at the center of the bushing, is perfectly at the center at the bushing. No concentricity. Okay, no concentricity meaning that no variation between the center line of the journal and the center line of center position of the journal, and also no variation on the center position of the bearing. Okay, so when eccentricity is 0, h naught becomes c, because you see here, you see as I illustrate here, if okay, the c naught, okay, the h naught is minimum film thickness, so it will become the clearance. Relate here with the picture, relate with the picture here. So since e and becomes 0, e naught becomes 0 as the load is increased and the journal is placed forward, downward, the limiting position reaches h naught becomes 0, meaning it touches, it touch the bushing. Okay, and e it becomes c, electricity becomes c. That is when the journal touch the bushing. For this condition, the eccentricity ratio is unity, hence h naught equals to c minus e. Okay, dividing both sides by c, we have h naught over c equals to 1 minus e. Okay, familiar with h naught over c, it is represented in the graph. Okay, design optima are sometimes maximum load, which is load characteristic of the bearing, sometimes minimum parasitic power loss or minimum coefficient of friction. Dash line appears on figure 1216 for minimum maximum load and minimum coefficient of friction, so that you can easily favor one for maximum load or minimum coefficient of friction, but not both. You cannot choose both, whether you choose maximum load or minimum friction. So this slide is talk about the dash line in the figure. Okay, and then this coefficient of friction chart, figure 12.8, we will see in when we come to figure 12.8. So here is figure 12.16. You have learned in the example previously what is going what the previous slide telling about is this dash line, this dash line. Okay, this dash line is in the condition where you must choose uh, within maximum load or minimum friction. Okay, the condition is that the center line is sit perfectly on the journal sits perfectly on the center of its position for the bearing and also the journal. Okay, now students, in this example 12.2, we are going to learn about using table 12.18. Okay, figure 12.18. Okay, figure 12.18 is dealing with friction. Okay, so using parameters given in example 12.1, determine the coefficient of friction, the torque to overcome friction, and the power loss to friction. Okay, so using the all information in table in example 1, okay, uh, the Stormofin number is 0.135. Okay, if you don't remember, just pause this video, go back to the screen time for uh, as Stormofin number 0.135, and the L over D equals to 1, and from the figure 12.18, you will find on the y-axis is R over CF equals to 3.5. Okay, and coefficient of friction F is F over equals to 3.5 C over R. You get 0.07. And then friction torque of the journal using this equation, torque equals to force WR. You remember torque, the equation for torque is general. You may find torque in other subject also. torque equals to force times radius. Okay, so in this case, the load is 500, the radius is 0.75. From the previous example one, you get this value, and then friction is 0.07, you get 2.62 pounds inch. The power loss in H power is Tn over 1050. This is from the equation. Okay, you get 0.075 horsepower, and that all expressed in BTU per second. BTU stand for British Thermal Unit. Okay, British Thermal Unit. You can Google what is British Thermal Unit. And the power loss H, the power loss is represented by the word H. Okay, 2 pi Tn over this equation, and then you get 0.0529 BTU second. Okay, let's see figure 1218. Okay, figure 1215. Remember the the x-axis is the sum of number. So again, I will emphasize you must remember the equation for sum of number, which is r over c power 2 u n per p. Okay, you make if you make mistake, everything will be mistake. From the beginning until the uh, last question, you will make mistake. Don't make mistake on some of the number. Again, and then extrapolate the graph. You get value 0.135. It is like this, and then extrapolate until L equals to 1, L over D equals to 1 here, and then you go here. Okay, you get this value for the coefficient of friction. Remember, is coefficient of friction is the equation R over C F. Okay, this is R over C F. Okay, and then R, you want to find friction. This is the friction that you want to find. Okay, you already get know the radius of the journal is 0.75. The clearance you will know from the previous example and everything, and then the value you get, you can get the friction 0.07 everything in this equation only. Okay. Okay, now we're talking about lubricant flow. From example 12.3, continue from example 12.1, determine the total volumetric flow rate Q and the side flow rate QR. Okay, QS. Okay, side flow rate is QS. So the solution is to estimate the lubricant flow. Enter figure 1219 with S equals to 0.135 and L over D equals to 1 to obtain the Q ratio. Okay, the Q equals, over RC and L equals to 4.68. Okay, how do you get this number? It is from the graph that in the next slide. Okay, total volumetric flow rate is Q equal to this equation, and you get to 0.217, and the cycling rate QS over Q equals to 0.65, and QS is equal to QS equals to 0.12 inch per second. So all the data that all this data you will get from figure 12.19. Here is figure 12.19. Okay, so again, you must know the Sommerfeld number. Okay, I must emphasize to you, never forget Sommerfeld number, the equation R over C power of 2 U N per P. Okay, if you do it wrong at the first question, you will do wrong for the all question. Okay, and then here you can see the on the y-axis is the flow rate on the equation QRCL. So you want to know Q, and the information for general radius, the C clearance, the all these other equation at below, you already know from the previous question. So put in the equation, and then you get the answer. Okay, the same again. This is 0.135. Just extrapolate the graph. 0.135, let's say like this. Okay, go for everybody over equals to 1. Okay, then go here. Okay, just like that. then you get the answer here, and then put in the equation here, and then you will get the Q. So the same goes for here also. You already know the Summerfield number. Okay, extrapolate it to 0.135. 0.135, you extrapolate it to become 1, and then go like that. You will get the uh, the value, and you already know Q. You already know Q from the previous calculation, from the previous graph, and then you will now know the QS value. The side leakage QS is from the lower part of the bearing where internal pressure is above the atmospheric pressure. Okay, the leakage from a fillet at the general bushing external junction and is carried by the general motion to the top of the bushing where the internal pressure is below the atmospheric pressure and the gap is much larger to be sucked in and return to the lubricant sump. Okay, what does it mean like this? When the lubricant, okay, when the journal is going down, okay, the bottom one has a higher atmospheric pressure, okay, upper one has lower atmospheric pressure. So when the pressure differences and when it go up, okay, when it go up, the lubricant going up also. So meaning that some part of it will come out, okay, some part of the lubricant will come out, okay, and then what the maintenance guy have to do is to regularly uh, put the lubricant, okay, adding the lubricant, okay. This is what we have to do. Okay. So the slide continue with film pressure, which is we will use the table 12, the figure 1221. Okay, the maximum pressure developed in the film can be estimated by finding the pressure ratio P per P max from the chart 1221, location where the terminating maximum pressure occurs. Okay, so using uh, example 12.4, the using the maximum parameter, the parameters given in example 12.1 determine the maximum fillet pressure and location of the maximum and terminating pressures. Okay, so entering figure 12.21, okay, which is we will see in the next slide. Okay, Sommerfeld number 0.135, L over D is equal to 1. We find P per P max equal to P 0.42. And the maximum pressure P max is therefore given here 529 psi. So we get from, again, we get from another graph, figure 1222, uh, the theta max is 18.5 degrees and terminating position is theta P naught is 75 degrees. So we see what these figures, both figures show. Okay, here is figure 1221. Okay, shows the maximum film pressure. Okay, so again, Sommerfeld number is important. Here is the Sommerfeld number. Never forget this equation. Okay, and within this Sommerfeld number in x-axis, the same procedure. You know 0.135 is around here, and you extrapolate to become this 1, L over D equal 1. Then go here, and you can see the this value, you get 0.42 estimate. So if you give answer more or less the same, it is acceptable, okay, within the range. And then minimum film pressure, okay, in the y-axis, you know P over P max, PSI, you get this. You can see clearly if you have the book with you, you can see the clearly, okay. So P equal to P max, you already have known P, you've known the value for P from the equation. For example 12.1, you calculate the value P, okay, and then uh, put in this value and you get P max, okay. Okay, from figure 1222, here is figure 1222. You can see if you extrapolate 0.135, okay, you can get for the terminating pressure for the equation is 75 degrees here, and then from this you get 18.5 degrees here. Okay, these both values for the terminating filler pressure, the degrees, meaning that when it is rotating, okay, the location when it rotate goes up, goes down, it is at this predetermined angle that we become the pressure. Okay, it will get uh, the minimum and maximum terminating film pressure. Okay, so here is an example 12.1 until 12.4 demonstrate how Remandi and Boyd charts are used. It should be clear that we do not have general bearing parametric relation as equation, but in the form of charts. Moreover, the example was simple because the steady state equivalent viscosity was given. We will now show how the average film temperature and corresponding velocity is found from the energy considerations. Okay, now we are going to talk about lubricant temperature rise. The temperature of lubricant rises until the rate of which work is done by the journal of the film through uh, fluid pressure is the same as the rate at which heat is transferred to greater surroundings. The specific arrangement of the bearing plumbing affects the quantitative relation. Okay, you can see figure 1223. Okay, in the next slide, lubricant sum, internal or external, to the bearing housing supplies lubricant at some temperature. Okay, TS, this is the temperature of the sum. Okay, to the bearing analysis of the temperature. So at temperature Ts equals to T1, the lubricant pass once around the bushing and is delivered at higher lubricant T1 at uh, at temperature variation to the sum of the lubricant leaks out of the bearing and mixing cup temperature. Okay, temperature 1 and plus the variation of temperature minus 2 and is returned to the sum. The sum may be a keyway like groove in a bearing cap or a larger chamber up to half the bearing circumference. If it can occupy all of the bearing cap of a split bearing such a bearing side leakage occurs from the lower portion and is sucked back into the ruptured film arc. The sum could be well removed from the general bushing interface. Okay, so from most of the general bearing, they have a groove to make uh, for all the side leakage will go down into that groove, and when you do the maintenance, you can throw away all the excess lubricant. And this is what the slide means. Okay, okay, figure 1223, you can see here schematic of a general bearing with an external sum with cooling lubricants make one pass returning before returning to the sum. Okay, you can see here uh, the way that you learn from this is when you see this uh, the short form Q S Q I T T1 everything, study the picture, study this picture, where is the location, and better still if you can print this page from the book, also from this slide you can print this page, and this page will be with you all the time when you study this topic, because when it refer to the some terms you may know where is the location of the system. Okay, do it until you understand, and then okay to you. Okay, so using the sum as a control region, we can write an enthalpy balance Okay, using T1 as the datum temperature, give H loss equal to this equation. Remember the word enthalpy from other subject, which is the subject thermodynamic. Okay, thermodynamic is also among hard subject for you to understand. The same as fluid mechanics, the same as this subject also very hard to understand. Eventually we will understand. Okay, because this topic, when it involves temperature, you also must have basic knowledge from thermodynamic subject. Okay, so the thermal energy loss at steady state H loss is equal to the rate of work. Thus, when the film H loss equal to W equals to 2 pi Tn J. The torque J is FWR. Okay, the lowest internal pressure is W equals to 2 pi Rn. Okay. Again, another tips to remember is the torque equation is the same for all subject, meaning that on the only term that may be different is how they use the symbol. Okay, here they are using WR. Another subject you may find FR, but the principle is the same, force times the radius. Okay, and this subject also added friction to it, so friction times force times radius. Okay, so multiplying numerator, increase clearance given by energy loss, H loss. Okay, this equation. Okay, from equating, arranging the result, you get JP, CP. You can know this equation to see the common petroleum lubricants is like this. Density is this, CP is this, and then J is this. Okay, and then you get 9.7 temperature range over the pressure PSI. Or you can eventually derive all this thing, you can get from equation 1215 like this. And this is the figure 1224. Okay, the figure 1219 and 1220 combine to reduce iteration table lookup. Okay, so this is some, if you like a shortcut, you like to say shortcut. Okay lah, you can say as a shortcut. Okay, uh, for lubricant. Okay, to find the lubricant, to find the value for this, where the temperature range is temperature rise in Fahrenheit, and PSI is the bearing pressure in PSI. The right side equation 1215 can be evaluated from figure 1218, 1219, 1220 for various Sommerfeld number and L over D region to give figure 1224. It is easy to show that the left side of figure 1215 can be expressed as this equation, where temperature range C is expressed in Celsius and pressure MPa is expressed in MPa. Okay, the ordinate figure 1224 is either K 9.70. I can read all this question, which is not surprising since both are dimensionless in proper units and identical in magnitude. Okay, so in solution to the very problem involve iteration and reading many graph and introduce error. Figure 1234 reduces 3 graph into one step in the proper direction, meaning that uh, you in doing this, okay, lot of graph you must read. Okay, lot of graph you must read, meaning that, in other words, you cannot make mistake at the first graph, especially at the Sommerfeld number. If you make mistake, do the equation wrong, you may be wrong all the way. Okay, must remember the Sommerfeld equation all the time. And this is the interpolation over the ratio other than given the chart. Raymond D and Boyd have provided the following interpolation equation, where y is the desired variable from interval, okay, interval D, and y4 is the variable corresponding L ratio respectively. Okay, then again, this is the interpolation. You should know the basic. Okay, if you know the basic, you know how to do this, no problem. That's all for this video. It's nearly 1 hour video explaining about how to read the graph. It is a necessary step to do. Usually in examination, uh, we lecturers we must give uh, all the tables. Okay, lecturer must give all the table, and you should know how to read the table. Beginning from the beginning of the table, 12.14 something until the end of 12.23, all in sequence. The most important thing is you know how to read, you know how to calculate sum of the number, and then you see the y graph. Okay, the y graph, and you extrapolate correctly. Use your ruler, use your ruler to extrapolate, to see the graph x and see the graph y. Okay, and when you get the number, you see the y graph, what is the value for y graph and everything. Okay, that's all for this video. It's a very lengthy video. Try to understand. Okay, better see this video with book beside you, so that you can understand, and you can see the graph. Okay, so I wish you the best. Thank you very much.